Hello, everyone. My name is Justine Cocchi, and I'm a program manager on the Azure CosmosDB team. I'm joined today by Gautam Chandra, the Senior Director of Software Engineering at Sam's Club. We are excited to talk to you about modernizing applications in Azure today. The requirements of modern apps have changed, and the world has changed with it. Zero downtime is more important than ever, as downtime can often lead to revenue loss for businesses. You want to make sure that your application can respond to spikes in user traffic with predictable performance and low costs. And also, delivery velocity is extremely important. As the world changes, you want your app to be able to change with it and respond to trends quickly and with confidence. As you think about modernizing your application, it's important to keep several design principles in mind. And these design principles really will underpin all of the other concepts and patterns that we talk about today. The first is business requirements. And when you think about business requirements, just like your application, your requirements are not a monolith. Think about what are the requirements for each component of your system and design resiliency and all of your modernization strategy with those business requirements in mind. Thinking about resilience, this is important. Your workload should continue to function even if there's reduced functionality or something goes wrong. Designing for recovery is extremely important. You should be able to anticipate and recover quickly from any failures that might happen. Are there self-healing mitigations you can put in place to protect yourself? And lastly, design for operations. You don't just build your application once and forget about it. You have to continue building repeatable and consistent processes and engineering systems that will help you on your modernization journey. Now, let's take a look at a couple foundational concepts. First is fault tolerance. This is important to ensure that no single failure takes down the entire system. And you can plan for various failures and think about the failure modes that can happen along your application. Consider a simplified e-commerce website. We've got a front end, a couple of APIs hosted in AKS, and our data is in Azure CosmosDB. What if there's networking failures? What if one of your pods goes down or something happens with your database? It's important to think about your failure modes before they happen so that you can plan and be ready to react. Now, we want all of our services to be highly available. High availability ensures uptime and continuity with redundancy in various layers of our application. Let's consider what this looks like for our AKS cluster. So we have our 3 APIs. And in Azure, we can leverage availability zones to ensure that our nodes are actually spanning across zones. Availability zones in Azure are separated groups of data centers within a region with independent power and cooling and networking. This ensures that if one zone goes down, you still have other zones ready to serve traffic for your application and avoid service disruptions for your users. But availability zones are great. What if the whole region goes down? You can have regional replication. These are all components of the high availability strategy that will ensure your application is resilient and available. We all know things go wrong, so it's important to have disaster recovery plans. How are you going to fail over, and what are the requirements for those scenarios in various parts of your application? We typically think of a couple of metrics when we think of our disaster recovery plan. As time goes on, if a disaster strikes, there's 2 key time periods to think of. The first is the time before the disaster. This is a period where you may see some data loss. Maybe data hasn't fully replicated, and it could be lost in a disaster. The time after the disaster is a potential downtime, where it might take some time for your services to come back online. These are measured in terms of 2 key metrics. The first is RPO, Recovery Point Objective, where is the period of data loss actually, and after the disaster is RTO, Recovery Time Objective. Now, with all of these concepts in mind, I'd like to hand it off to Gautam, who will discuss Sam's Club's modernization journey.
All right. Thank you, Justine, for setting that stage. Good morning, everyone. So for the next 15 minutes, we are going to look at how we modernized our commerce platform at Sam's Club. So we are going to talk all these 4 segments. First, we will talk about the engineering principles we laid out as a foundation. Then we will talk about the transition itself. Then we are going to talk about how we achieved availability, resilience, and scale on that platform. And finally, how we use Azure products to achieve that. Let me introduce you to the digital core that we have at SAMS, which is our omni-commerce platform. This is the foundation for all our customer journeys. And it is omni-channel architecture. What do you mean by that? That means we have in-club customers to serve and also online e-commerce customers to serve. And this enables end-to-end shopping journey from login to checkout, a usual retail flow. And then this is achieved by integrating all the services and subdomains of a typical e-commerce system. Well, this was the past. This is a starting point where we have this bulky monolith, classic spaghetti architecture, disconnected monolith systems. We had one for e-commerce, one for in-club, not designed for scalability. There is no reuse. There is very difficulty to achieve an omni-channel experience in the setup. You go to club, in the store, you will see few promotions and discounts, which you will not see in e-commerce, right? The release management was extremely painful. And as you guys might know, the holiday period is our biggest event. That's where our business thrives. And how do we scale the system, right? We bring all the engineers to a big hall doing pre-scaling, manual throttling, traffic, and fine-tuning everything just to prepare for that event, hoping that nothing happens. It's a very tightly coupled system, meaning one small failure at any corner can bring down the entire website. So there's a saying that in this setup, through years, we have become the experts of creating the most innovative sorry page, so that during the Thanksgiving, we can show it to the customers when we are saying you cannot shop. That's not resilience. We got to do something about it. We got to prepare for the future. This is the transformed state. We have one Omni backbone, no channel silos. That means we broke that monolith apart into cloud-native omni-channel microservices. So now we have independent services that can scale and have its own resources with clear boundaries. We can ship faster with very less risk. And also, the blast radius is reduced to services. And another funny conversation that we used to have is every year before events, before the holidays, we review with our senior architects, and they used to ask, hey, what's your blast radius for this change? And we used to say, what do you mean blast radius? There is only one blast radius. It's the entire website. Something happens, everything goes down. But not anymore, right? So we know it was a very difficult task to achieve that. So we got to go back and figure out what are the goals? What are we really going behind? We wanted to replace crowded war rooms, manual tweaking the last minute with dashboards, automated alerting, and all the goodness of SRE world. We got to be event ready. We got to ship faster. We got to be tolerant to any failures that happens in one corner of the system or any part of the system. We got to be highly available. And the best part is, in a monolith, it's very hard to monitor all the parts at the same time. With this new system, we wanted to make sure that we are able to monitor each and every subsystem at the level of system stats, at the level of service stats, the DB performance, how are their connection pools working, everything. All right, so now goals are good. How do you bring it and make it part of our engineering culture? So we established something called SAM's 5 pillars of excellence. All the architects, all the engineers we have at SAM's came together. We built this. You can see quality, which means focus on automated testing, integration with automated CI/CDs, security, principle of least privilege, and zero trust. APIs, databases, resources, no matter what. Firewalling at the network layer. All these comes under that bucket. Observability. What do you mean by observability in a high-scale, end-to-end e-commerce platform? That means valid dashboards, defined SLOs for each services, and then monitor each and every system, hook in the alerts, and if anything breaches your error rate that we have agreed, breaches the budget, you get a call to the on-call person who is holding the phone. We got to be event ready at any point in time. That means we should be able to take the 10x scale without any manual steps. And always we got to use the best possible patterns that is there in the industry to achieve scalability and availability. We should be able to test it on a near production similar system at any point in time with a click of a button. And it all rests on Azure and Kubernetes. So now we adopted domain-driven design standards to divide this monolith. We aligned our architecture with the business that we execute to identify clear boundaries that created distinct subdomains. So now, for each subdomain, we need ownership. So we build an ownership model, service ownership model. One person is accountable for a particular service, and they are responsible for implementing all the 5 pillars of excellence for that subdomain. And both combined, DDD and service ownership, enabled us to achieve great operational excellence today. Well, this is the reference architecture. So now we looked at the goals, we looked at the 5 pillars of excellence, we looked at the high-level blueprint architecture. Now, these are the highlights of how we implemented it. Cloud-native microservices architecture, multi-region active-active setup for high availability and best-in-class fault tolerance. We use Azure pair regions as a core part of our disaster strategy so that if an outage happens, the shift to the healthy region is smooth. So this is how we implemented that architecture. Multi-region AKS, independent microservices, valid dashboards, alerts hooked into the on-call notifications, resilience patterns like circuit breaker, Saga for distributed transactions and recovery, bulkhead patterns to isolate the failures, and all this while implementing the best industry standards of SRE. So we knew resilience is not an accident. We got to design for it. So these are the 4 main things that we continue to do. One is failure mode effect analysis. We look at each component and we put a score 1 to 10 to identify the risk before they become outage. Circuit breakers, we use it to stop cascading failures. At both service level and the application level we'll look at in the upcoming slides, but for platform also, it makes a lot of sense to stop these cascading failures. Self-healing mechanisms in AKS, we use liveness readiness probes and HPA, horizontal pod scaling, for making sure that the pod that came up is ready to take traffic. If it is not, take it out of the traffic rotation. Failure isolation using a bulkhead pattern using dedicated namespace and connection pool. This protects the services from noisy neighbors. Let's say if I'm running a job on membership analysis, promotion engine is not impacted or card is not impacted. If one part fails, it's kind of contained. So now coming back to the security from the 5 pillars of excellence, we use OPA, policy as code, and open policy agent. It runs as a sidecar container with Envoy parallel within the same pod next to the service pod, next to the service container. These policies are crafted using Rego and managed in Git. So with the webhook triggers, if you push in a PR with the updated policies, it's immediately pushed to the pod. With that deploying next to each other, the performance is extremely high between the service and the policy. With this, we can do app-to-app authentication, PII control. I don't see your card, you don't see my wallet, that kind of a thing. And then header constraints. I can say, hey, if there is one particular reduced access for a client, I can kind of say, no, you cannot call this API or that. I mean, that kind of a management we are talking about here. All right, so that's part. So far, we have discussed about how the platform was modernized. So let's switch to the service. So now we have the platform, and we got to build the structure on top with all the microservices. And this was a tedious task. Somebody is checking out, somebody is signing up membership, somebody is logging in. It's a live service. We don't want to impact the member. So it's like, we always say that this was a project where the flight the plane is midair. We got to change the engine. We got to refuel. And at the same time, serve coffee to all the passengers without disturbing them. It was a very difficult task. So what did we do? We decided that we will use strangler fig pattern. That means old and new APIs run parallel for a smooth and gradual migration. The clients, when they are ready, they can switch over. 100% backward compatibility to prevent any client disruptions. Our business was always like, OK, build this feature, OK, while you're migrating. Migration is good, but build this feature. OK, so that's how we achieve that. Data migration, we use CosmosDB change feed for most of the cases for the continuous sync. It helps us bring in one-time backfill of the data and then the continuous stream of changes without any downtime. So it allowed us to cut over the services one by one and with no downtime. So all of these resides, again, on multi-region AKS with circuit breakers, fallbacks, backups, bulkhead. So now talk about CosmosDB. We lean heavily on CosmosDB, and most of our CosmosDB accounts are deployed in multi-region. How do we plan for scale and resilience? We have multi-availability zone, which will help us from regional outage. And what happens if within a region something goes wrong? We have PPAF, per partition automatic failover, which will help the partitions to recover when there is a local failure happening. It promises RTO and RPO of less than 2 minutes, which is perfect. We also looked at our SDK configuration, and we review it consistently when there is a new version upgrade. We fine-tune timeouts, retries, preferred region configurations, mostly to keep our traffic local. As in, if you are local traffic, local meaning if you are from East Coast, your card checkout, the whole stack should happen at the East Coast. We should not send you to the West Coast and bring it back. Also, read hedging will help us with the parallel lookups if there is any latencies on the server side. So not every service needs 5 nines of availability. 5 nines of availability takes a lot of design, a lot of time, a lot of fine-tuning, and it's got to be your muscle memory. So let's say if I have a setup tool where I am setting up promotions or something which is not time critical or data critical, we can have it at single region. At that time, 4 nines are OK. But at the same time, for membership, wherever you are shopping, you got to be checking if you have an active membership, are you in good standing, no fraud, that kind of stuff. We need 5 nines. So this is how we, based on the needs of our applications, we choose one of these configurations. Simplified version, but there are many ways we can configure this. Justine is going to talk much more detail of this. Well, that's NoSQL. So there are services that needs relational guarantees. For that, we use Azure SQL Hyperscale. It has elastic storage up to 128 terabytes. We don't need to keep adding the storage. And at any point in time, if there is an immediate need of scaling, it can scale the compute and storage independently. That's fantastic. For resilience, we use failure groups. Fog is a good feature that we use. Pretty impressed by that, by having a geo-replication asynchronously. And also, it provides one connect string for your code to talk to this. And the failover from an unhealthy region to a healthy region happens without anything. It just happens behind the scene. You don't need to make any connection string changes. All these things made our DR operations pretty simple. All right, so now, how are we tying all these things together? So how do we achieve 5 nines end-to-end? Active computes in AKS, data layer redundancy with CosmosDB, fog groups in Azure SQL, readiness-driven traffic orchestration, and also protection patterns like circuit breakers, bulkheads. And by doing all these things, the math just simply works. If we combine multiple 9 services across multiple regions, the composite availabilities easily go beyond 5 nines. And all these are good. How do we practice it? We do regular holiday readiness drills, fully automated, so that we are ready. All these theories work together well for achieving 5 nines at any point in time. All right, now I'm going to go back to my desk and show you a demo. Always been told that don't trust slides, show it, right? So we are going to see what happens when an entire Azure region is going to go down, first on the service layer and then the database layer. I got to do a little magic here to just pause because it's a crammed dashboard. Let me walk you through this. So we have an application deployed in South Central and West Central, West US, 10 pods. That's the green boxes that you see. The first row is JVM metrics and the CPU usages on the right for all the pods that we have on both regions. The next row is about APIs. The left side is about write, the first three, and the second part of the second row is about read APIs. And the last row is about DBs. I wish it was simple, but I'm sorry. This is a live dashboard that we use. Last minute put up this demo, so please bear with us. Let me walk you guys through this. So there is a service deployed on South Central West US. It's backed by an Azure CosmosDB, and it's a single write, meaning it can write at a time to only one region at a time. But the reads are active, because this service is read heavy. Let's roll it. Yeah. So now you're going to see things that I have talked. We are going to see a similar traffic surge that we usually experience during an holiday event. You can see, while it's pumping up the traffic, you can see the second row. You can see all the traffic, and all the write traffics are on the South Central because that's our write primary region. Second row right side, you can see the read traffic is evenly split between South Central and West US because it is an active configuration. You got to keep staring at that 0%. And if you guys see any 0.01%, raise your hand. That means we are doing good if you see 0. So now we have an outage on the service side, the compute side in SCUS. You're seeing the pods going down from 10 to 3, now down to 2 and 0. So what's going to happen is you're going to see South Central traffic is going to go down, and West US is going to pick up the traffic seamlessly. Traffic gracefully shifting to West US. This just highlights that there is no service disruption for either writes or reads. This is what we wanted. This is what we have been trying to achieve. You're going to see some momentary spikes because the traffic is going back and forth and connections being exhausted and reestablished during the retries. So now the outage hits the database. So our primary SCUS is hit, and now we got to failover to the west. Again, you will see that the new connections, the new requests are seamlessly transferring over to west, and there is no service disruption even now. Again, there is a tall spike just because of that cutover. It's a momentary spike, and then you will see everything settling down. And voila, 0 impact during either of these outages. And this is a live system. We just recorded from what we have, the completely automated CI/CD. So what did we just see? We saw complete outage of compute region and then a database failure. Our active compute, our health prop traffic routing, and the multi-region data layer within the CosmosDB help us stay alive all the time without any service disruption. All work together to prevent any impact. And that's all. Justine, over to you now.
Thanks, Gautam. So you just heard about many architecture patterns that Sam's Club is implementing and that they implemented along their modernization journey. And I want to really dive deep into those patterns and how you can implement them in your own applications. And to do that, we're going to revisit our much simplified e-commerce architecture. So we have our front end on Azure Web Apps. We've got a couple services in AKS. We have the Products API, which allows users to browse products on our site. We've got the Shopping Cart API as they add items to their cart, and an Orders API that allows them to create that order and make their payments. Now, I've got all of my data stored in Azure CosmosDB. So why did we choose CosmosDB? CosmosDB is a distributed NoSQL database that is really built for resiliency and scale. It can easily horizontally scale out infinitely because it adds more partitions to serve your needs as you either add storage or increase your throughput. While it scales out, it can maintain consistent performance. We have a single-digit millisecond SLA for reads and writes, regardless of how large your container grows. This is extremely important because performance is important for our applications to ensure that as users are browsing our site, they can see the items that they need quickly. CosmosDB also has built-in resiliency. You can achieve RPO of 0 with strong consistency, meaning that there is 0 data loss. You can also achieve RTO of 0 with multiple ways of active-active, and we'll look at a couple active-active configurations in just a minute. Now, I'm using CosmosDB for this example, but if you have a relational database or relational data, expertise in SQL, there are also plenty of great SQL options that will also allow you to build scalable and resilient applications. I want to talk a little bit about Azure SQL Hyperscale, which you heard Sam's Club is using in their application. This really allows you to scale out to meet the demands of your application. It has independent storage and compute, allowing you to add read replicas or increase your data footprint. And all of this can be done in an extremely cost-effective way. There's per-second billing with serverless in Hyperscale. All right, so now that we talked about the services, let's talk about the architecture patterns and the principles that we're trying to achieve for each one. We're going to isolate our critical resources with the bulkhead pattern. We're going to protect against failing remote services using circuit breaker. We'll compensate failed transactions with the Saga pattern. All of our services have their own independent data stores, so it's important to maintain this consistency. We also want to build in regional fault tolerance. We can do that with the active-active pattern. And lastly, we'll see how the cell architecture helps us achieve system-level isolation. Starting with the bulkhead pattern gets its name from bulkheads in a ship. They're basically partitions in the ship's hull that mean if water breaches one zone, it doesn't sink the entire ship. Similarly, in software engineering, this is really important, right? We don't want a failure in one service to take down our entire app. We can implement the bulkhead pattern with microservices. We've got 3 microservices here. And let's say we lose one of them. Customers can still browse our products. They can still add to carts. We don't have a full failure just because we have experiences in one area. Now, we also want to implement the circuit breaker pattern. The circuit breaker helps us protect against cascading failures. Just like a circuit breaker in a house will prevent a surge in electricity of creating a fire, circuit breakers can help prevent failing services from taking down your entire system. The circuit breaker pattern is implemented as a state machine, and we can illustrate this with our Orders API. Now, one of the things the Orders API does is it's responsible for taking payments. And unfortunately, we're using a flaky payment service, so sometimes we experience errors here. When requests are flowing through to our payment service, this is when the circuit breaker is in its closed state. Of course, when a circuit is closed, that means electricity can flow through, so requests are flowing through to our payment service. But we want to keep track of this because if we see too many failures, we want to give the service the time and space it needs to actually recover. So let's get a failed request counter. And by the time we see 5 requests, we want to intervene. We can start a timer, and now our circuit is in the open state. As the open state, that means electricity can't flow through and requests can't flow through. So no requests are going into our payment service for this period of time. After the timer, we can enter the half-open state. This is basically a trial state that allows us to make a test request. If it succeeds, we can go back to close, and our request can continue flowing. Now, I want to show you how easy this is to implement in code. So I'm going to switch over to a demo application, and we can see how it's implemented. In my demo application, I am using a .NET Blazor web app, and I've implemented this with .NET Aspire. .NET Aspire is a cloud-ready stack for building production-grade applications, and it also gives you a lot of defaults and things that you don't need to worry about configuring, but they just come for free by using Aspire. If you've used it before, you might be familiar with this line, which is adding our service defaults. Now, I'm going to step into this so that we can take a look at what we're doing here. I've actually created a slightly modified version of this standard service defaults to really illustrate the circuit breaker pattern. As you can see here, we're first going to configure a bunch of defaults for various things, including OpenTelemetry, health checks, etc. But what I want to focus on is the resiliency pipeline for our HTTP client. Now here I'm adding a custom resilience pipeline to only demonstrate the circuit breaker pattern. We're going to have a sampling duration, we'll look for a certain failure ratio, and we want to have a minimum throughput. However, the default service defaults in .NET Aspire actually sets up a resilience pipeline of a ton of strategies that can all work together, from a rate limiter, total timeout, retry, circuit breaker, and attempt timeout. However, it's very difficult to demonstrate the effects of a circuit breaker when you've got all of these other strategies. So in my application, I've only enabled the circuit breaker in my custom pipeline. I'm going to swap over to my website, and it's a very simple order form, as you can see. I'm just going to go ahead and submit an order. I'd love a new raincoat. It was raining this morning. So as we submit this, we'll see that we're making calls into our services. Now, we got a server error, and that's because the flaky payment service that I'm using is hard-coded to fail 33% of the time. So as I continue submitting orders, let's see how our circuit breaker can protect against these cascading failures. And as we keep submitting, we should be able to trip our circuit and get it into the closed state. I'm feeling lucky, so I get a lot of successful orders in a row. And here we go. We've hit the circuit breaker open. So this really protects us against overwhelming that downstream service and giving our flaky payment service some time to recover. So now that we've seen that there are failures in this system, we want to make sure that we can have consistent data across all of these distributed microservices. And the Saga pattern really helps us do that. We can issue compensating transactions to help us ensure our state is consistent. And we can do this without any really tight coupling or distributed locks, two-phases commits, anything like that. Taking a look at how we've implemented the Saga pattern here, we have our orders API. So we know our orders here is responsible for making payments. But we also have that products API. One of the things the products API is responsible for is updating our inventory in our products database. Now, when we get a failure, how does our products API know that there was a failure so that it can make the proper inventory adjustments? We can use an event queue. And this allows the services to communicate without that tight coupling. When we get a failure in our orders API, it emits a payment failed event into our event queue. The products API can read change feed in CosmosDB to read any events that might be relevant to it. When it sees that there is a payment failed, it can issue a compensating transaction with the Saga pattern to actually release that inventory. So we have a resilient application. We're able to have consistency across services, but what if there's a regional failure? I really want my app to be highly available, so I'm going to implement the active-active pattern. In the active-active pattern, multiple regions are simultaneously handling traffic. So if one goes down, the other, it can automatically continue serving your users. Let's look at how we implement this in our system. So now you see we've still got our setup with our web app, our AKS, and our CosmosDB, but now we have a replicated version in West US. So East US and West US. The way this active-active pattern is implemented is different for various types of services. Our services like AKS are stateless APIs, meaning we can actually just provision copies of them in each region. They don't need to be kept in sync because they're all stateless. So this works great, and AKS Fleets really helps us manage this deployment and make sure that everything is consistent across all of our regions. But looking at our other service, CosmosDB, this is a stateful service. We need to make sure the data is actually replicated. Imagine the experience, you're shopping the website, you're adding to your cart, and then disaster strikes, you're routed to West US, and your cart's empty. You don't want that, right? so with CosmosDB, we can replicate the data, and CosmosDB handles all of this automatically for you. There's actually two ways that you can implement the active-active pattern in CosmosDB. The first is with the multi-writer pattern. This means multiple regions in CosmosDB are accepting both read and write traffic simultaneously. This gives you an RTO of 0. There is no downtime because other regions are available to accept traffic if one goes down. Your RPO is roughly the time it takes to replicate your data across regions. If you have a single writer setup, you can still achieve the active-active pattern. And this is with a new feature in CosmosDB called per partition automatic failover. What this allows is while you still have a single primary write region, if any partitions in your container are experiencing issues, you can fail over at the partition level. And it's automatic, so the SDK will automatically handle this routing for you, and it will happen in less than 2 minutes. So this is an awesome option for the single writer case, and still maintaining that high availability even in that scenario. The last pattern I want to cover today is the cell pattern. So with the cell pattern, this provides system-level isolation. Let's say you have a multi-tenant application and you wanted a copy for one of your tenants. Maybe one of them is large and you want to make sure it's isolated. So we still have our East US, West US setup for tenant 1, and we can provide a copy of the full architecture for tenant 2. Another way this is very commonly implemented is for geographical cells. And this is seen all throughout Azure. Here's an example from the ARM team. So the ARM team used to have a single monolith, which created a single point of failure and caused a lot of issues. ARM is a foundational service in Azure, so we want it to be highly available. They moved into the cell architecture using geographically located cells. So you can see they have a cell for the Americas and a cell for APAC, and within the cell, there's still cross-region replication to ensure high availability. All right, so we've got a bunch of resiliency built in, but what if there's a sudden spike in user traffic? We want to make sure that our application is resilient and doesn't go down if we see, extra throughput. That's what we want, right? We all want more users. And each of these services have scaling built in to let your application seamlessly react to these spikes. Now, with CosmosDB using autoscale, it will instantaneously scale up within 10x of your requested throughput. As a scale out, if you need more partitions, it will also automatically add that for you. With autoscale, let's say you experience a spike in traffic to one of your partitions, that partition can scale up within its 10x throughput, but the other partitions are only scaled to the level that they need. This allows it to be extremely cost-effective while still giving you that flexibility to handle all of these spikes. Other services, like Azure SQL Hyperscale, are also built, as the name implies, to be very scalable. Now, we talked a little bit about Azure SQL Hyperscale and how it's independent scaling for storage and compute. So this really demonstrates how that happens. On the compute side, let's say you need extra read throughput. You can add up to 30 replicas for reading, and this will allow you to handle higher traffic. On the storage side, you can scale up to 128 terabytes. So this really allows you to react to the needs of your application. The last service I want to talk about is scaling on your app side for AKS. There's also many options for scaling in AKS. With the cluster autoscaler, you can use either horizontal or vertical pod scaling to ensure that your node pools are large enough to handle these spikes in traffic. At the infrastructure level, you can implement node auto-provisioning. This works at the lower level, and it allows you to actually provision the infrastructure that's required for your given application. It uses efficient bin packing to ensure that the infrastructure you're deployed on is right-sized for your needs, and instead of having idle cores from a misconfigured system. So we've seen how important resiliency and scale is for modern apps. And it's also really important to think about the maintenance and monitoring of these applications. If we look at the application development lifecycle, we've spent a lot of time in planning and development. We could give a full talk on every single one of these subjects. I'm going to skip testing and deployment for a minute, and I really want to focus on maintenance. Now, maintenance is important for ongoing resiliency. It's not a one-time effort to modernize your application. You need to make sure that it's modernized and also available over time and reacting to anything that may be going wrong. So how do we do that? Observability is really important. You saw how Sam's Club is using Grafana to observe what's going on in their application and ensure that they have those resiliency built in. There are three main pillars of observability that will really help us here. The first is metrics. Metrics helps us to identify trends in our application. You can monitor things like CPU, memory, latency to see if there's any trends that you might want to address. There's also logs. Logging is extremely important for getting those deep insights. You can see specifically what's going on, stack traces, errors, things like that, that will really help you debug the problems once they've been identified. And lastly, we have traces. Distributed tracing in applications like this is extremely important so that you can understand the request flow and the user journey, making sure that everything is actually flowing how you expect. So let's jump back into our demo, and we can see how easy this is to implement. So flipping back into my .NET application, now we mentioned that we're using .NET Aspire. And with Aspire, one of the things that I love about it is it gives us the Aspire dashboard. The Aspire dashboard is really your one-stop shop for observability. And let's take a look at some of the traces of this application. If I click in one of my request flow that I had earlier, we can see what's happening in this site. So we've got our post request here. We are calling the order service, and we're posting an order. The first thing is upstarting into CosmosDB. CosmosDB uses OpenTelemetry to emit a bunch of attributes about each of your requests. OpenTelemetry is quickly becoming an industry standard for observability and is a great way to get really the deep information about what's happening in your application. I can see that I'm contacting West US 2. This request costs 11 RUs, and a bunch of other information that might be relevant for debugging my app. I can also see this call to my flaky payment service that, again, is hard-coded to fail. I really need to use a more reliable payment service for my app. And flipping into code so that we can see how we've actually configured this, we have our OpenTelemetry built right into our service defaults. .NET Aspire is an opinionated framework, meaning it sets up all the best practices for you so that you don't need to think about it every time that you configure your app. If I look at how we've actually configured the OpenTelemetry for CosmosDB, I'll flip back into my order service. We can see I'm using the .NET Aspire Cosmos integration, and I'm able to automatically turn on key factors for my application. I'm able to turn on tracing, and I can also set some options. So here I've set some threshold options for logging. I am able to set separate thresholds for point operations, so single item operations, and non-point operations, which may take a little bit longer. Now here I've set my thresholds extremely low just to make sure that we get some logs, but I recommend that you look at thresholds that make sense for your application. So you can get the logs when you need them, but you don't have overly verbose logs that you're just paying for no reason. Now this is showing you all of this in .NET Aspire, but you can also, for live production development, easily pipe all of these things into something like application insights so that you can get insights into your live applications. So let's review what we went through with this modernization journey. First, we looked at some design principles that are important to keep in mind throughout this entire process. We implemented resiliency patterns that helped us achieve isolation of our services, regional independence, and making sure that our system is also duplicated. We looked at scalability features that really help us protect against spikes while still keeping our costs low and maintainable. And lastly, we looked at ongoing monitoring and maintenance and how important that is for actually debugging your applications. Now, lastly, I want to leave you with some resources so that you can learn a little bit more about resiliency and some best practices for your applications. And I also want to highlight some sessions for the rest of today at Ignite. Thank you so much. I hope you enjoyed this session.